Okay, so this is lecture 11 of our M254. And today we're going to continue our discussion on the EM algorithm. So in the beginning, I want to talk a little bit about the homework problem, which is regarding the EM algorithm for fitting the Gaussian mixture model. So some of you emailed me regarding the convergence of the algorithm. So I can say that if your algorithm is coded correctly, there shouldn't be a convergence problem. So to be exact, here in the E step, you are going to use the same formula for computing the tau IT, which is the conditional expectation of the latent variable Zi, which is equal to 0 or 1, given our data and given the current parameter estimates. So in the formula, which is based on the Bayes rule, you are going to, in your homework, you are going to replace this part. The density of xi given zi equals 1, you're going to replace this by the Gaussian density for f1, the distribution when zi equals 1. And this part is due to be the gamma, which is the proportion of zi equals 1. In the denominator, you're going to have a density with zi equals 1 and the density with zi equals 0. So you're going to have two terms in the sum in the denominator. So if your calculation is correct, based on this formula, you can see that every term is non-negative because the numerator is just one of the two terms in the denominator. So you know that the denominator should be greater or equal than the numerator. So this ratio, tau IT, should be between 0 and 1. So if your code doesn't show that, there must be some issue. And then given those tau IT, you are going to use them in the M step, which is the formula based on the MLE of the complete likelihood. So what you replace is, if you compare these two things side by side, what you compare is you replace the ZI by the tau IT in every formula. And that's how you're going to optimize the parameters in the iteration, in the next step. And then you come back to the E step. So that's the hint for that homework problem. And for sanity check, you may want to see if you input the true parameter values as the initial values into your algorithm. Well, if your EM algorithm is coded correctly, then the algorithm should stay at that true value. So in other words, you should add convergence immediately. And if that doesn't happen, it means that there must be something wrong with the algorithm. So yeah, that's just a hint. So last time we said, okay, the EM algorithm, why it works. There are two important facts. One is this important Jensen's inequality for a convex function or concave function. So they have the same property with opposite signs. So to really see the sign or the direction for the inequality, my suggestion is to draw the figure. This is the one that goes, so that this one is the convex function, and this one's the concave function. To help you know which one is which, you can just remember, okay, probably log function is the concave function. So if you remember that, you know the shape of the log function, then you can know the shape of the convex function. I think that's just easier for you to not confuse each other. And then you can draw a straight line, and you can see, okay, in this straight line, I'm having the expectation of the fx, okay? This is the straight line expectation of fx. And what's on the curve is the f of expectation of x. That is, you take expectation first, and then you put it into f. So that's the left-hand side. So you can see if the function is convex, we will have f ex less or equal than e of fx. And for the concave, it's the greater or equal than. So with this, then we know, okay, we're going to use this property so that you can imagine what's inside here is the likelihood. And you see, if we take the likelihood, so go here. So you see, the likelihood itself is just depending on the observed data x, okay? And how do we write it? We write it as the log of the density of x given beta. But we know it's actually easier to write the complete data density. And so we introduce the latent variable z, and we call x and z our complete data. So we know to go from the complete density to the x only density, we need to integrate our z. So we have here, but this integration itself is not an expectation yet. We need to make an expectation by introducing some density function of z, so that you see we divide this joint complete density by qz, we call this density qz of z, times qz. So then we created a case for expectation, because whenever we multiply a function of z times the density of z dz, then this integral can be regarded as expectation of the function of z. That's what we have here. Okay, so we're treating z to the following q, and then this integral becomes expectation of this thing, fxz, given about divided by qz. So here the z is the random variable. We are taking its expectation, and the expectation taken over density q. So now we are in the case we have a log of an expectation, because log is a concave function. So if we look at here, then the log of an expectation is on the curve, which is greater or equal than the expectation of the log. That's what we have here. By Jensen's inequality, we have the expectation of log of the ratio. And because log of the ratio can be written as the difference of two logs, so we have log fxz beta minus log qz. Okay, and we see that only the first term is related to our parameter of interest beta. Beta is only in the first term, but not in the second term, because second term is something arbitrary. Any density q can be used here. So we found a lower bound of the log likelihood here. And the second part for optimizing the log likelihood is to optimize or maximize the lower bound. And we're going to use this property here. That is, if we have a lower bound, g, that's easy to maximize, and g and our target function f, they are tangent at this value x1. So that means, sorry, at this value x0, my bad. So that means we can just maximize g to update the value of x, to go from the current x0 to the new value x1 that maximizes g. And we can show that this new value x1 can give a value larger for f. So fx1 will be greater or equal than fx0. This is the derivation. We know that by lower bound, fx1 should be greater or equal than gx1, as always. And because of the maximization, gx1 should be greater or equal than gx0. And then because of the tangency, gx0 should be equal to fx0. So that's why we are actually updating the value x to make the f value bigger. So given this part and this part, we are going to use this fact so that we can optimize this lower bound to increase the value of log likelihood. So log likelihood is our f, and beta is our x, and this lower bound is our g. That's what we're going to do. But one thing we're not done yet is that for this expectation, the q is arbitrary. We chose it to be a density of z, so we can make this an expectation. But how do we choose q? How to choose q? This is the PDF density of z. And don't forget that here the z is n-dimensional, we have z1 to zn. So how to choose this q? To do this, we are going to use this tangency. Okay, so that's the requirement for this optimization to work. Okay, to make the lower bound tangent to the L beta x, our target log likelihood function at the current value of beta t. Let's say we are in the tth iteration already, and we want to find a lower bound, add this value so that the lower bound is tangent to this. So in other words, we are going to have, that is, let me push this out a little bit. So that is, we need to have L beta T x equals the lower bound, which is here. So expectation of z following Q density of log f x z, the joint density at beta t minus log qz. Okay, we need to satisfy this. And to make them equal, you see, the key thing here is to make the Jensen's inequality equal. To make the Jensen's inequality equal. So this requires, which requires the Jensen's inequality to be equal at beta t. So this is the only place where we don't have equality in the whole derivation. So when is this equal? So looking at this curve, looking at this example, when would any value in the line, in the curve, be equal to the line, be the value in the line? So when will these two values be equal to each other? That's when the line segment has length 0. You can imagine if we shrink the line to a point, then the line and the point, when the curve, they coincide, they collide. So that means we have equality. So in other words, let me say here, the Jensen's inequality becomes equality if and only if our x is a constant, which means that expectation, so x is not a random variable, so the expectation does not change it. That is, we have the expectation of x equals x, and also the expectation of fx just equals fx. That's what we have for a constant. So this is for the case when the f is not linear, of course. If it's linear, then it holds for sure. So this is for strictly concave or strictly convex f. Okay, so for strictly convex or concave, when f is not linear, then to make the Jensen's inequality be an equality, we need to have the x to be a constant instead of random variable. And of course, here you see our f is the log function. So we know the log function is strictly concave. So to make this inequality as equality, we need what's here, a constant. And by constant, we mean that it has nothing to do with z anymore because the expectation is taken over z. So whenever the ratio inside doesn't have z at all, it is considered as a constant for this expectation. Okay, so therefore, what we need is this. So we need this ratio fxz given current value of beta t divided by qz to be something not involving z. So z needs to be gone. So what this suggests is that we can write qz to be proportional to fxz given beta t. Okay, by proportional, we mean that there can be a multiplier, but the multiplier must not involve z. And we see that by using this form as no, so by basically this is a function with z involved, but it's a joint function of x and z, right? That's the joint density. But now we're going to just have Z to be of the same form subject to a multiplier so that it becomes a valid density. So how do we do it? It's basically to normalize this, right? So essentially, this is just equal to, I can write it out exactly. So this will be just equal to this dividing by a normalization constant over all possible values of Z. So this dz. So if I can do this integration, I can show that this QZ is a valid density because whenever I do the integration for Z, I will get a value 1. That's a valid density. So you see, this tells me the exact form of Q to make Jensen's inequality become inequality at the current value of beta t. And this is what? If you see here, this numerator, this denominator, after I do the integration of Z, I'm left with the marginal density of X only. Okay, so I know this is exactly what I have here. The integration of Z gives me the marginal density of X. So basically, this is the probability, this is joint density divided by marginal density. Let me write it down. X, Z, beta t divided by fx beta t. So this is exactly, this part is equal to the probability density function of Z given X and given the current value of beta t. You see, so I basically obtained the form for Q, the distribution of Z that I need to make Jensen's inequality become equality is to set Q to be the posterior, or I should say, the density, conditional density of Z given X and given beta t. That's it. So in other words, to be exact, I should put T in the superscript of Q because you can see as my parameter value changes, the Q function, the density function for Z should change accordingly because beta t is here. So that's the EM algorithm. We basically show that to apply this optimization principle, that is, we want to optimize a tangent lower bound to update the value so we can increase the function value of the log likelihood. We just need to set the Q to be this conditional density of Z given X and beta t. We obtain the lower bound, okay? That's the E step. Let me write it down. So to summarize, in the E step, we compute the lower bound, okay? Compute the expectation of Z, and we know that, and this is in the Tth iteration. So we carry the T with us. We compute the conditional expectation of Z given following X and beta t. This is our Q for our complete log likelihood. So this is the log density, right? We can also treat this as the log complete likelihood of beta. And please note that here, the beta should remain as beta. So what I mean is that here, when we compute the expectation, we are just taking Z to be taken over by the expectation. Okay, that's the lower bound. But you know, the beta remains as beta as an argument. Just as here, what we mean is that given you have the G function here, the G function has argument as X that can vary, but you just need to make sure that G and F are tangent at X0. So this Q function in this form is for the tangency. So that's why for the tangency, we need beta t here for the Q. But inside, the beta is still an argument that can change, just like in our log likelihood. So we have here, and we also have the log QZ, okay? So basically QZ here would be this value. That's our QZ. So I just put it here. So fxz beta t divided by fx beta t. You see, this part has nothing to do with z. That's the first step. We compute this. That's the lower bound. So you see, this is what we call a lower bound of the log likelihood of beta given x. And these two things are tangent at beta t. So what we mean by their tangent at beta t is that when I replace this beta by beta t, and then replace this beta by beta t, they become equal to each other. That's what we mean by tangency. So just keep in mind that this lower bound is still a function of beta, and beta is right here. Okay, in the M step, we are just going to apply this principle to maximize the lower bound G. So here we want to maximize this part, okay? So find beta t plus 1 that maximizes this lower bound. That's how we are going to update the beta value to beta t plus 1. And then you see, to maximize the lower bound, the only term that involves beta is the first term. The second term has nothing to do with beta. So it is equivalent to say the beta t plus 1 should just maximize or be the argmax of the first term. That is expectation of z given x and beta t of log f x z beta. So we can drop the second term. So that's why you see, because in the end step, we just need to maximize the first term, and the second term doesn't matter. Therefore, as a result, in our next iteration, the E step, we just need to calculate the first term. We don't need to worry about the second term. Okay, so just to simplify things, we just do the iteration as follows. And also for the first term, to make it more clear, this is equal to the log likelihood, complete log likelihood of beta given x and z. That's the thing we can easily write down based on the complete data by assuming the latent variables are observed. So to summarize, make it simpler for you. So in short, the E step is to just compute. Let's give this a name. So let's just say that in the E step, we give this term, how about we just use the G, okay? The G function in the T iteration of beta, we just compute it as the expectation of Z given X and beta T of the complete log likelihood of beta given X and Z. That's the first step. And the E step. And in the M step, we just update beta T plus 1 by maximizing this function GT. Okay, so this is just a notation. So you see, now it's clearer. In the first step, E step is to compute the expectation of Z given X and beta T current value of the complete log likelihood. Given this complete log likelihood expectation, we maximize it in the M step to update the beta value. This is the general EM algorithm. And why do we have in the previous example that, looking at here, why do we only need to compute the expectation of ZI instead of the conditional, instead of the complete log likelihood? The reason is here. You look at the complete log likelihood. Let me put that page here. You look at the complete log likelihood, okay? This is what we need to take expectation for in the E step. Looking at this formula, which is also this also applies to your homework problem. You see that once we take expectation for Z given X and parameters, that expectation will enter the sum and become the expectation of ZI. So that simplifies the thing. To compute the expectation of the complete log likelihood, you just need expectation for Zi, and that solves the problem. And then you can replace the actual Zi by the expected Zi. And that's why we have that special form of EM algorithm in our previous example and in your homework. Does that make sense to you? So this is a little complicated. We need several components to really make sense of the EM algorithm. But maybe you need some more time to understand it fully, or probably even after this class. But I want to say that the take-home message is that the simple version of EM algorithm we derive in the class, which has the meaning of imputation, that is, we replace EI by expectation of ZI, that simple version is only a special case of the EM algorithm. In a general version, in the E step, we need to take the complete log likelihood, and then we need to take its expectation for ZIs. So the expectations for ZI given X, the observed data, and given the current value of the parameters. Okay, that's the E step. And the purpose is to construct a lower bound for the log likelihood we want to maximize. And the M step is to maximize the lower bound so that we know the updated parameter value will drive the log likelihood to be larger. And that's based on this fact. That's based on this simple fact in optimization. Okay, so that's all I want to say about the EM algorithm. Do we have any questions before we move on to our next topic? Okay, great. If you have any questions, don't hesitate to ask. So the next thing we're going to say is also relevant. It's called the MM algorithm. And so I think everyone in UCLA should understand this before you graduate, because the MM algorithm was developed by Dr. Ken Lange, who is a UCLA faculty, a retired faculty, and this is one of his prominent work. So I think the name is so interesting that it has two interpretations. So it can be considered either as, okay, minorization, maximization. This is the version we talk about, okay? So this is the case when we have a lower bound, which is called minorization. And then we maximize the lower bound, we can increase the value for the target function. So this is one way to interpret MM. The second way is to think of this as majorization and minimization. Minimization. So this is to minimize a target function. So you can think of this as negative f. So if you want to maximize f, it is equivalent to minimize negative f. And then in that case, what you can do is that you can find the upper bound of it. And the upper bound is tangent to f at the current value, just as we have here. And then you minimize that upper bound so that at the new value, the negative f value will go down. So everything can be carried over directly by adding the negative sign. So once you add the negative sign, you change the direction of every inequality. So yeah, we already did it. So we already explained the minorization, maximization. This is exactly what we have here. So this is the MM algorithm. So for MM algorithm to work, it's for the case that you need to find a nice, not an easy to optimize lower bound. That's the thing. So the f is usually a complicated function which you cannot simply find its maximum, no matter local maximum or global maximum, by taking the differentiation. That's not possible if f is too complicated. Or even if you take the differentiation, finding the solution is difficult. So that's the case where you want to use an iterative algorithm to find the solution numerically, or maximize it numerically. So if you can find a nice lower bound, G, that you can simply maximize using a closed form, then you can apply this MM algorithm to maximize the f. So I'm not going into detail here because if you just Google MM algorithm, I think King has some very nice slides online, which has some examples about the implementation. So you can check it out there. So this is just an optimization problem. It has nothing to do with statistics. We just use optimization as a tool to find like the parameter estimates as MLE, right? So if we convert the problem into an MLE problem, then the MLE part is an optimization problem. But just bear in mind that this is the mathematical tool and it has nothing to do with statistics, that's all. Okay, so that's all I want to say. This concludes the model-based clustering. You know, like I said, model-based clustering relies on a probabilistic model to help you do the clustering. But to really have the probabilistic model fit to your data, right, you need the parameter values. To estimate those parameter values, we use the MLE. And because in the MLE, we don't have complete data, there's missing data or latent variables, so the MLE is not straightforward. And the EM algorithm provides a convenient way for us to deal with the MLE problem for the likelihood with missing data. So just to emphasize again that when we talk about the likelihood, we define the likelihood as the drawing density of the observed data given parameter. It's not the complete likelihood. So likelihood and complete likelihood are two different things. Please don't confuse the two. For complete likelihood, we take the missing data as observed, but this is not something we can write down or we can implement. It's just conceptual. So therefore, you cannot maximize the complete likelihood to estimate your parameters, because as we have seen, the MLE of the complete likelihood will involve Z, and you cannot compute those because ZIs are not known. So therefore, you want to maximize the log likelihood based on the observed data only. But the optimization problem is usually not easy. Like we have seen the brute force approach, right? That's computationally very intensive. So then the EM algorithm provides a very smart way to optimize the log likelihood via this MM approach, minorization-maximization. So that's just the whole story. All right, so that concludes this model-based clustering part. And this also concludes our clustering part for unsupervised learning. Now, our next part is about the dimension reduction, another very important technique for unsupervised learning. Okay, so you can check the MM algorithm detail in our notes if you're interested. So now let's move on to dimension reduction. So this is another important technique for unsupervised learning. What does it do? So in the dimension reduction problem, it's used for two purposes. One is for visualization. And I think maybe I should say three purposes. The other is to actually combine or reduce the number of dimensions for downstream analysis, or to actually get rid of or get around the curse of dimensionality. Usually when we have two large dimensions, we have some issues. So let me just talk about this later. Yeah, about what do we mean by curse of dimensionality. And the third thing is to remove noise. Hopefully by reducing dimensions, we can keep the biological signals while removing the unwanted noise. So these are the three purposes of doing dimension reduction. Then what do we do exactly? So our data points are denoted by p-dimensional vectors. So as we have seen, so to help you concrete this idea, you can think of each data point as a cell, as in our single cell data. And it's encoded by p genes. Usually for our human data, p is equal to 20,000. So each cell is a 20,000 dimensional vector. And that's a pretty big dimension. Our human mind cannot really process a 20,000 dimensional space. We can only imagine 3-dimensional space, right? Anything beyond that is beyond our perception. But mathematically, we can have a very large high-dimensional space. So our goal is to find a much lower dimension, let's say D, or I should say K, which is much smaller than P. We use this notation to mean much smaller. so that we can encode our data into Z1 to Zn, still n data points, but with k dimensions only. That's what we call a dimension reduction problem. But how do we find the Z1 to Zn? We must preserve some property, right? That's the goal. So next, we're going to introduce several dimension reduction methods that preserves different properties in the x1 to xn to find the projection, Z1 to Zn. And also in machine learning, some people call this as the embedding. Low dimensional embeddings of high dimensional points. You can see this term. The first and simplest method I'm going to introduce is the PCA, Principal Component Analysis. Short as PCA. So one thing to pay attention to is the spelling. So for the principal, you don't want to spell as PLE instead of, so the correct one should be PAL, because these two terms have different meanings. Just pay attention. I saw some misspellings often. So what do I mean by principal component? So each PC can be regarded as a linear combination of the original P dimensions. So let's put it in mathematical notations to be exact. So our data matrix is of this form. We call it X. It's n by P. We put the data points of our observations in rows, and we put the features or dimensions in columns. So we have two ways to write it. The first way is to write out the observations as n rows. So we often write as lowercase x1 transpose to lowercase xn transpose. So each xi itself, as we have here, is a p-dimensional point vector. Now we are going to put it as a row. So we take the transpose, right, and stack them horizontally. Another way is to write them out as columns. So when we do that, we will have p columns. We have x1 to xp. So then each column is an n-dimensional vector. It encodes the coordinates my n observations have in that dimension. So we can have these two ways. And what we want to do is we want to find another matrix Z, which is m by k. So I'm going to still write my n observations as n rows. Now they are Z1 to Zn transpose, each being k dimensional. Or we can write down the columns Z1 to Zk. So these are the new k dimensions, not the original p dimensions. And for each dimension, we have the coordinates of the n observations. Okay, that's the low dimensional matrix. Our goal is to find this. So then what does PCA do? So of course, as I said, PCA is a linear dimension reduction. Okay, so by linear dimension reduction. So by linear, I mean that each new dimension is a linear combination of the original P dimension. So write it out. I have Z1, the first column, equals to, I'm just going to use the notation that is some weight for the first original dimension, which I call phi11, plus phi21 for the weight of the second original dimension, plus 2 phi p1 times the p dimension. That's the first new dimension obtained. It's a linear combination of the original p dimensions. And I continue. For the zk, the last new dimension, it can be written as phi1k x1 plus phi2k x2 plus phi pk xp. Okay, so I actually have k linear combinations, and this is how I write it out. But if I want to make it more succinct, I can write this in a vector form. So in a vector form, I can just write this as the matrix X, right, multiply a vector, I call it phi1. So the phi1 is just a p-dimensional vector as phi11 to phi p1. I stack those together, and by matrix multiplication, this right multiplication exactly means for each column of X, I multiply it by the corresponding entry in phi1, and then I take the sum. That will give me Z1. So this is a very succinct way of writing this. So similarly, for this one, I can write as X times phi p. And phi p is also a p-dimensional vector. It is phi, oh sorry, not phi p, phi k. Phi k is a p-dimensional vector with elements as phi 1k to phi pk. Okay, so this matrix form can save us a lot of space. And I give these weight vectors a name. So I call these phi 1 to phi k as k loading matrices. K loading vectors, K loading vectors. Okay, so by loadings, we mean, okay, each entry is the loading of my original dimension in that new dimension. So we can call phi11 to phi p1 as the loadings in the first new dimension, and phi 1k to phi pk as the loadings in the last new dimension. And I also have a name for those Z1 to ZK. So Z1 to ZKs, they are called K-score vectors. So please note these are p-dimensional and these are n-dimensional. So by score vectors, I mean each, let's say Z1, it's the scores of the n observations in the new dimension 1. And ZK contains the scores of the n observations in the new dimension k. So I have the score vectors and I have the loading vectors. So that's what we want to have as a result of dimension reduction. Once we have the loading vectors, I can immediately have the score vectors just by this multiplication. But then the question is how to find phi 1 to phi k. That's the question to be answered by PCA. So in PCA, what we really want to do is to preserve the variance. Okay, so we want to preserve the variance of my n data points x1 to xn across the original p dimension. That's what we want. And I want to preserve the order, the variance in a decreasing order. That is, I want to have the first new dimension preserve the most variance, and then the second new dimension to preserve most of the remaining variance, and so on. So I'm going to have a decreasing order. And also, furthermore, I forgot to say that for these k-score vectors, we can also call them KPCs. K principal components. These are the score vectors. So I know that there's some confusion or ambiguity in terminology. Some people refer to the loading vectors as PCs, but I think the consensus or the majority of people think we should call the score vector as PCs. So in other words, when we have the first PC, it is the first score vector, the transformation of our n data points into the first new dimension. Okay, so the goal of PC is to have PC1, which is equal to x times phi 1, preserve the most variance Okay, and we know this x phi 1 itself is a n-dimensional vector. So then what do we mean by preserving the most variance? So if we write it out, okay, so if we write it out, so x phi 1 is by our notation z1. Okay, and just for your convenience, let me write out it as this z11 to zn1. So in the scalar form. So its variance should be the variance based on these n values. We know it should be determined by 1 over n or n minus 1. Doesn't matter that much here. I from 1 to m. Then we have zi1, each entry minus its mean. The mean will be the average of those things. So I just call it 1 over n summation of z j1, j from 1 to n. The average, I put it inside square. That's the variance. And we know that with this center term here, it's a little complicated. So for simplicity, okay, for simplicity, we just set this term, the center, the average of those to be equal to 0. And this is equivalent to set, if we look at here, this is equivalent to set each column of my matrix X. I set each column to have center 0, because you see, as a linear combination, if each xi, x1 to xp, xj has mean 0, then zi would directly have mean 0. So you see, for simplicity, I set x to have column means all equal to 0. So this is just by shifting. I shift every column so that it has mean 0. This can make me have this average of this zi1 equal to 0. So the variance here, so the variance of the first PC would become just 1 over n summation I from 1 to n. This becomes 0, so I have zi squared. Okay, zi1 squared. And this is what? I'm squaring each entry here. That's basically the inner product of zi. So this is equal to 1 over n zi transpose zi. So it's the transpose times itself. That gives me this. So therefore, to find this phi I is to maximize this variance. So what I mean is that the phi I should be found to maximize this zi transpose zi. I can drop this 1 over n. It's not affecting my observation, my optimization. So, and this is what zi depends on phi 1. So it's actually argmax to find phi y to maximize x phi 1 transpose x phi 1. Okay, if I continue, this thing to be maximized is actually phi 1 transpose x transpose x phi 1. I have this. Okay, that's the goal, to find the first loading vector. But I also need to have some constraint here, because I cannot let the phi I vector to vary freely. Otherwise, this can be as large as infinity. If you can imagine, I set every entry of phi 1 to be infinity, right? That doesn't make sense. So I need some constraint on this phi 1. So look at here. This phi 1 as a vector contains the p weights. So it's reasonable to require this phi 1 vector to have a norm 1, Euclidean norm 1 or L2 norm 1. That is, I can require phi 1 squared plus 2 phi p1 squared to be equal to 1. So add a constraint. That is, I need to have the phi 1 squared plus phi 2 1 squared plus plus 5p1 squared equal to 1. And this is equivalent to say phi 1 transpose pi 1 if inner product, which is equal to this, is equal to 1. And this is also equivalent to write that the L2 norm of phi 1 is equal to 1. Sometimes people drop the sub-index for 2 because at the 2 norm is just regarded as the standard norm, the standard type of norm. Okay, so we have this. So then the question becomes optimization problem. How do we find phi 1 to maximize phi 1 transpose x phi 1 subject to phi 1 transpose phi 1 equals 1? That's the optimization problem. And we know that this constraint can be incorporated into a Lagrange multiplier in the optimization problem. This is a standard technique. So what we do is that we just use that Lagrange multiplier technique. If you're interested in this, and if this is new to you, you can check the Wikipedia page to start with. So we're going to use this constraint as part of our optimization problem. So we want to find the maximizer of phi 1 and the constant lambda for this thing, phi 1 transpose x phi 1 minus lambda times phi 1 transpose phi 1 minus 1. So you see, because of the constraint, this term should be equal to 0. So when this is equal to 0, it's not affecting this part as well. Okay, so that's the Lagrange multiplier trick. And we just want to take differentiation against phi 1 to achieve the maximum, to solve this problem. That is, we set the gradient of this function against phi 1 and set that gradient to 0. And that solution will be the maximizer phi 1 for this whole function. That's what we want. And then what do we do? So if we take the differentiation against phi 1, so because here phi 1 is a vector, when we take differentiation against a vector, we call the result a gradient. And the gradient has the same dimension as phi 1. The gradient will be p-dimensional. Each entry is a partial derivative. So we can take the derivative against the first dimension of phi 1, second dimension of phi 1, and the p dimension of phi 1. That gives us the gradient vector. So if we do that, we can solve the first one. That will give us 2 times x transpose x phi 1. This requires some matrix calculus, actually. And we have posted a matrix cookbook. Or maybe not for this class, sorry. I'm going to post that on the CCLE so you can check it out. So it actually contains all the command or all the formula you need. But I suggest that to really understand this, probably catching up with linear algebra will be something very worthwhile. If you really want to master data science, I would say linear algebra is a must. But the must. But let's come back here. So that we take derivative here, we get this. For the second part, I get 2 times lambda phi 1. So you see the two are still p-dimensional vectors equal to 0. And you see, I have something interesting. I cancel the 2, move this to the right-hand side. I have x transpose x phi 1 equals lambda phi 1. And lambda is just a scalar, okay? Lambda is a scalar. I can say it's positive scalar. And this is a p by p matrix, x transpose x. A square matrix. And then what's this? This tells me, if you have learned of eigenvalue and eigenvector, this tells me, okay, lambda is an eigenvalue of x transpose x. And phi 1 is the corresponding eigenvector. This is the definition of eigenvalue and eigenvector. That means if you multiply a left multiply a vector by a square matrix, and if this is equal to just put a linear put a scaling factor multiplied to the vector, then we see, yeah, this scaling factor is an value of that square matrix. That's what we use here. So what else? Given this, okay, given this part equals this, then our target, phi 1 transpose x phi 1 becomes, using this as the replacement, becomes phi 1 transpose lambda phi 1. And because lambda is a scalar, I can move it before, so to the front, I get this. And because I have the constraint, phi 1 transpose phi 1 equals 1, I get lambda. So you see, I get this as a lambda, and I want to maximize this. And lambda must be an eigenvalue of this x transpose x. So together, this tells me, okay, lambda must be the largest eigenvalue of x transpose x. So we solve the problem. So essentially, this optimization problem becomes an eigen decomposition problem. We just need to find the largest eigenvalue of this matrix, and that will be equal to the variance of PC1. So not divided by n, of course. We ignored n. But if we ignore the 1 over m, this part is just the largest eigenvalue of this. And then if we do the eigen decomposition, we will have the corresponding eigenvector. That will be the first loading vector I need. So essentially, PCA is equivalent to eigen decomposition of x transpose x. And often we write the eigen decomposition of a square matrix of this form. So we often write this as, I'm just going to stick with that, V times lambda times V transpose. Okay, so what is the V? What is the lambda? So the V is just, I can say that here it's a P by, okay, so maybe I just make it simpler. So I would just say this is just, okay, so what should I say? The P by, it's a P by K, yeah, let me put it here. So let's just say this. So if we have the X, if X has K independent columns. So please note that here the independence is the linear algebra independence, it's not the probability independence, which means that I just need K columns to explain all the columns. Or we can say this is the column rank. So if all the P columns are linearly independent, which means that I can now take any column and write it as a linear function of the remaining P minus 1 columns. If I cannot do that, I say all the P columns are linear independent, then the column rank is just equal to P. So I can say the matrix X has full column rank. But here I'm just assuming, okay, this has K independent ranks. Oh, probably I don't need that. Okay, so, okay, let's do that. Okay, K, column rank K. Then I can write this lambda. So then what I do is that I can spell out this P, this V matrix as probably I need the column vectors. Okay, so I just write it as V1 transpose to VP transpose. Let's do it that way. Each one is K-dimensional, okay? And the lambda is a diagonal matrix. I call it K by K. So I can order the non-zero eigenvalues. Let's say the matrix has, so okay, basically the matrix, if it has K column rank, then this X transpose X should have K non-zero eigenvalues. So the number of eigenvalues of this X transpose X is equal to the column rank. And then the V transpose is K by P. It's just V1 to VP, okay? This is what we call eigen decomposition. And these V1 to VP are Oh my bad. No, not right. I need to write down that the thing. Sorry. Forgive me for this. So I should write V in terms of the eigenvectors here. Yeah, that's the correct way to write it. So this V is P by K. Okay, so this stays the same. But what I will write it here is phi 1 to phi K. Yeah, to be consistent with our notation. Those loading vectors will be here. And lambda K by K stays as lambda 1 to lambda K. This is also here, the non-zero eigenvalues. And then V transpose K by P, it will be phi 1 transpose to phi K transpose. Okay, yeah, this is much better. This is the eigenvector, this is the eigenvalue. And then you see by matrix multiplication, when I do V times a diagonal matrix lambda times V transpose, then I would have X transpose X. This will be something very interesting for diagonal matrix. It's like these are weights of inner products. I will basically have phi 1 times lambda 1 times phi 1 transpose plus 2 phi k times lambda 1 times phi k transpose. You see, this is very interesting. This is a p by 1 vector. This is a 1 by p vector. P by 1 vector, 1 by p vector, and this should be lambda k. So we call this an outer product. You know, so outer product is that you use a vector. A vector's outer product with itself gives you a matrix, while a vector's inner product with itself gives you a scalar. So here we're doing this outer product, and people call this what? Sometimes in machine learning, you will see people call this a rank 1 matrix. This is it. So even though you can get a P by P matrix out, but if you verify it, this matrix has only column rank equal to 1 and row rank equal to 1. In other words, each column is just a linear factor of the other column, linear multiplier of another column. And each row is also a linear multiplier of another column. So you can actually see this is a rank 1 matrix. And this is also rank 1 matrix. So eigen decomposition is so nice that it allows us to decompose this P by P matrix, X transpose X, into the sum of K rank 1 matrices. And this K is the rank of this. Okay, so in other words, I'm just talking about the eigen decomposition problem, but this is the foundation of PCA. So if you think this is something interesting, it's very worth looking into. And another related concept is what we call SVD, singular value decomposition. I'm also going to introduce that briefly. So singular value decomposition, SVD, unlike the eigenvalue decomposition, this doesn't require the matrix to be squared. So this can apply to any matrix. And this is a general form. So I take my data matrix X to begin with. The general form of SVD is that I have it written as a U, which is, this is n by P. U is n by K matrix times a diagonal matrix K by K times V transpose a K by P matrix. V transpose is K by P. So this is something very interesting that we call the U as left singular vectors, V as right singular vectors, and D is a diagonal matrix whose diagonal entries are singular values. And so here we only keep the K non-zero singular values, which is equal to the column rank of X. So the same as the previous K. So if we write it out, then we can actually show that this is, so with this singular value decomposition, you can see that this will give me X transpose X, the thing I want to decompose for the PCA, equal to, I'm just taking U dV transpose times U dV transpose, okay? And after some algebra, I know this transpose will reverse the order, etc. So I can have V times D. So for diagonal matrix, it transpose itself times U make transpose times U D V transpose. And also for the singular value, we actually have some nice property. That is U transpose U for the left singular vectors. This will be an identity matrix k-dimensional. And also V transpose V is also an identity matrix k-dimensional. So we have those nice properties. And then you see this is identity, can go away. And D times D is the diagonal matrix by itself, it's squared. So I get V D squared V transpose. If you compare this with the eigen decomposition, you see the V is the same V. So in other words, the right singular vectors you obtain by SVD is exactly the eigenvectors of X transpose X. And then lambda 1 to lambda k is just the square of the singular values. So in other words, let me put it this way. So the eigenvalue of X transpose X is equal to the square of the singular values of X. Okay, so I'm just going to stop here. I just give you the most important results about SVD, eigen decomposition, and PCA. So to really understand linear algebra, I would strongly recommend a course which everyone can watch freely, maybe on iTunes, University, or Coursera, or YouTube. So it's actually a linear algebra course taught by a retired MIT professor, Dr. Gilbert Strain, S-T-A-R-A-N-G. So his course is the one I found most clear and illuminating. So if you're interested in linear algebra, this is the course to pick. Yeah, so these will actually explain all the things I said here, and it will try to make PCA make more sense to you. But of course, I know so many people use PCA without really understanding what's going on. So, but hopefully this can help you understand better. So essentially, PCs, I would say the loading vectors are the eigenvectors. To summarize, those messy stuff, we have to summarize the loading vectors are just eigenvectors of X transpose X. Okay, that's the first thing. And the second thing is that the variances of PCs is just equal to 1 over n times the eigenvalues of X transpose X. So each eigenvalue lambda I at lambda 1 is just equal to the variance of the first PC. After we divide lambda 1 by n, that's the variance of first PC. Yeah, so that's the second thing. And the third thing is because the eigenvectors themselves are orthogonal. So you know the loading vectors themselves are orthogonal, okay? So this will make any phi I transpose phi j equal to 0 if I doesn't equal to j. So any two loading vectors are orthogonal to each other. And this is another very important property. So yeah, I think that's all, PCA. That's the PCA I want to introduce. So it's a little bit more mathematical than what you see in a very introductory textbook, because they just tell you the intuition behind PCA. That in the first PC, you preserve the most variance in your data. Second PC is orthogonal to the first one, preserves the second most variance, etc. So that gives us the evaluation of the PC. How many PCs should we keep, right? The practical question. Number of PCs to keep. So this amounts to the variance we explained. So essentially, to plot the percent of variance, so this is called PVE, percent of variance explained, PVE. So it's actually the total variance explained by how much in PC1, how much in PC2, right? So using our formulation here, it's essentially this. So I'm going to say that given my Z1 definition, Z1 is the score of the PC1. Z1 is the PC1. So for PC1, I'm going to say, let me just write it here. So PVE1 for the first PC. So based on our definition, after centering, it's just 1 over n summation of Z I1 square, I from 1 to n. And this will be divided by the total variance in my original data matrix. So over there, I am going to have 1 over n still here. So it will be summation j from 1 to p and z from I from 1 to n x ij square. That's the variance in my original data, right? I'm basically taking the variance in each dimension for points 1 to n. I take the variance, and then I take the summation across my dimensions for j from 1 to p. And then finally, I divide by my number of data points. That's the variance. And you see the 1 over n can be canceled and canceled. That's the PVE1. And PVE2 for the second PC is similar. Summation I from 1 to n zi2 squared divided by the sum j from 1 to p, I from 1 to n, xij squared. So the denominator stays the same, but the numerator continues. So if you let k equals p, which means you don't do any dimension reduction, then you can fully capture the original variance. So that is, you can have the PVE1 plus PVE2 plus 2 PVEP equals 1. So you don't lose any variance in your original data. But that's usually not what you want, because otherwise it doesn't make sense, right? You're just transforming P dimensions to another P dimension. The only thing is that in the new P dimensions, the new dimensions are orthogonal to each other. So it's like you're transforming a non-orthogonal space to an orthogonal basis. That's it. It's just a basis transformation. But you are not doing any reduction. So therefore, usually we don't do this. We want to find the proper K to be reduced to. And hopefully the K is much smaller than P. So that's why we have this elbow plot, just as what we have for the clustering K-means problem, how to choose the K. This is also about K. This is a PVEK. And here we have the basically PC, the K here. So this is for PC1, PC2, up to PCK, right? So we can show how this changes. So we know their sum is equal to 1, and each one is a percentage between 0 and 1. We have 0 here, 1 here. So for example, we have PC1 explains a lot of the variance. So say 0.06 here, and PC2 jumps to say 0.3, and PC3 further down. So you will have the PVE goes down as your number of PC goes up. And also, a nice property about PC is that no matter what K you set, so the PCs will stay the same. Let's say if I set K equals 2, the PC1 and PC2 will be the same as if I set K equals 3 and go down to PC3. This is also guaranteed by the eigenvector property. So these are the first eigenvector, second eigenvector of X transpose X. So usually what we do is that we look at the K, choose K such that the summation of PVE1 plus 2 PVEK is about 80%. So usually we target that 80% as a reasonable amount of variance preserved and find how many pieces do we need. But still, this depends. 80% is not some golden rule. It's just something people think is a reasonable amount of variance. And also it depends on your data, right? We hope that the variance we capture are biological signals and the variance we lose are technical variance. So that's also a very tricky thing. So next time when we come back, we can tell you some example in single cell data where people show, okay, PC1, if we think the observations X1 to Xn are cells, they think PC1 is dominated by the cell library sizes. So it's about how many breeds you have per cell. That is highly correlated with PC1. But if that variance is not something of your interest, then you may want to remove that PC1. Okay, so we'll come back to this issue next time when we come back. And also, please start early with your final project if you haven't done so. Right, we are already in our week 6, and you're going to do your final presentation in week 10.